The world is full of unseen things, movements, forces, connections. Electricity is one such marvel. It powers our lives, it lights our cities, it carries our thoughts across distances. But what is this flow? How do we speak of its strength? We need a measure, a name, a way to quantify this invisible river. This measure has a name. We call it the Ampere, named after André-Marie Ampere, a scientist of great insight. He explored electricity's mysteries. The Ampere tells us how much electric current flows through a wire, a circuit, a device. It is fundamental, like the meter, or the kilogram, or the second. For a long time its definition was rooted in the world of tangible forces. The old Ampere had a specific form. It was defined in 1948. Though the idea was older, it spoke of an ideal situation. Imagine two straight wires, infinitely long, perfectly parallel, placed in a vacuum, far from all else. They have a negligible circular cross-section. A very precise theoretical setup. This was the stage for the definition. Now let current flow through these wires. The same amount of current in each. If the currents flow in the same direction, the wires pull towards each other, they attract. If currents flow in opposite directions, the wires push each other away, they repel. This is the magnetic force, a consequence of moving charges. The definition was precise. 1 ampere was that constant current. To understand the old Ampere, picture the lab. Not infinite wires, of course. Real experiments used finite lengths, coils of wire carefully constructed, instruments of great precision. Scientists worked to create the conditions, as close to the ideal as possible. The vacuum was important, to remove air which might interfere. The distance, 1 meter, was a reference. The force itself was incredibly small, 2/10,000,000ths of a newton, per meter of wire. Imagine the weight of a tiny mosquito, perhaps even less. Measuring such delicate forces is hard. It requires exquisitely sensitive balances, devices shielded from vibrations, from stray magnetic fields, from changes in temperature. The experiment was a delicate ballet. Currents had to be perfectly steady. Section 4. The unstable measure challenges of the original Ampere. The old definition, while elegant, had flaws, not in its theory perhaps, but in its practical realization. Achieving those ideal conditions was a dream. Infinite wires do not exist. A perfect vacuum is elusive. Even the Earth's magnetic field interfered. It had to be carefully shielded. These were immense technical hurdles. For any laboratory trying to realize the Ampere, the measurement itself was a source of uncertainty. Measuring that tiny force directly, with the necessary precision, was one of the hardest tasks in metrology. Metrology is the science of measurement. The instruments, like kibble balances, then watt balances, were complex and expensive. They required constant calibration and deep expertise to operate. This limited its accessibility. Because of these difficulties, the Ampere was one of the least accurately realized SI base units. Section 5. A universe of constants. The call for a new foundation. Science often seeks a deeper understanding, a view of the world based on fundamentals. The old Ampere was tied to an experiment, a macroscopic setup of wires and forces. But what if we could tie it to something more basic? Something inherent in nature itself. This was the growing desire, a shift in how we define our units, a move towards the constants of physics, numbers that appear universal. Consider the speed of light, c. It is a fundamental constant. The meter is now defined using it. The second is defined by atomic clocks, based on the unchanging properties of atoms. These definitions are robust. They do not depend on a specific artifact, or a difficult experiment that might vary. They are, in principle, accessible anywhere, if one has the right tools. The kilogram also underwent this change, no longer a piece of platinum iridium in Paris. Section 6. Counting charges, the Ampere reborn from the elementary. The new definition arrived in 2019, a landmark year for metrology. The Ampere was untethered from macroscopic forces. It found its new home in the quantum world. Specifically, it became linked to the elementary charge. The symbol for this charge is E. It is the electric charge carried by a single proton, or with opposite sign by a single electron. It is a fundamental constant of nature, a tiny indivisible packet of charge. The new definition fixes the numerical value of this elementary charge E. It is set to exactly 1.602176634 times 10 to the minus 19 coulombs. The coulomb is the unit of electric charge, and 1 ampere is defined as 1 coulomb per second. So by fixing E, and with the second already defined, the ampere is now precisely determined. It is a flow of a specific number of elementary charges, passing a point in a circuit, each and every second. How many charges is that? If 1 ampere is 1 coulomb per second. Section 7. Precision's new dawn, the ampere's enduring significance. The shift to the new definition is profound. It is more than just a technical change, it reflects a deeper understanding of physics. Our units are now tied to the constants that govern the universe at its most fundamental level. This brings stability and universality. The ampere, defined via the elementary charge E, is now as constant as E itself. Its value will not drift. It is woven into the fabric of physical law. Practically, this means greater precision. Electrical measurements can be more accurate. This benefits many fields, from advanced scientific research to the development of new technologies. Think of sensitive electronics, medical devices, quantum computing, all rely on precise control and measurement of electrical currents, voltages, and resistances. A more accurate ampere underpins this progress. The new ampere simplifies how standards are maintained.